Okay, I found my mistake in this derivation. You see here, when I was writing the probability density, the wave function squared, I had included this additional factor too. But when I take the square, it just disappears. So it will be corrected in the notes. Now, any questions on this momentum position uncertainty? Because there is one more type of uncertainty that, well, okay, let's see. Another perspective on the uncertainty principle. Let's say momentum position uncertainty. You see, such an uncertainty in the position and momentum, in a sense, also exists in classical physics. You see, the uncertainty principle doesn't tell us that we cannot measure the position and the momentum more precisely. Actually, what it tells us is we can measure the position and momentum up to that precision, which is not yet reached even in classical physics, even in classical measurements. You see, the problem over there is, let's say you have a particle, an electron, let's say. How do you measure its position? You send some kind of a wave. It doesn't have to be a light beam, but you send some kind of a wave. And look at the scattered wave. So what is the precision of such a measurement in the position? If you use a wave of wavelength lambda, you cannot measure anything, any position with a precision higher than lambda. So this is the most precise determination of the position of that object will be. If you use a wave, the wavelength limits your precision. Now, what is the wave momentum of this wave? This is h over lambda.
Why wavelength? Why not the time or the speed or I don't know. But why wavelength?
Well, you see, just imagine yourself in the sea. Okay? So if you have a larger wave, a wave with a large wavelength, well, that will not even see you. You have these large waves, they just hit you, when they pass you, nothing changes in your wave. So anyone who is observing that wave with a larger wavelength will not even know that you are there. So leave aside that measuring your size, such a wave will not even see you. But if you look at the ripples on the surface, well, the ripples will change their shape as they are crossing you. So because their wavelength is much smaller than you. So that's an example where you actually see this phenomenon. It can. Well, you see, the incident wave, let's say, it has this much momentum. Well, what you see, you are sending a wave that has a momentum, and you are expecting that wave to scatter. But that means the momentum of the wave will change. Momentum is conserved. That difference will be transferred to the particle, and so you are changing the momentum of the particle. And the change in the momentum of the particle will typically have a value h over lambda. Well, it depends on the angle, it depends on various factors, but the typical magnitude will be h over lambda. So delta p will be typically h over delta x in this measurement, or delta p delta x is something like h. But of course, this perspective, although it gives the same answer more or less, is radically different from the previous perspective though. You see here, in this perspective, we are assuming that the particle has a position and has a momentum. And we are saying that we can determine its position with this precision at most. then we are changing its momentum typically by this much. And interpreting the change in the momentum by how much we change the system. But this perspective has the concept that the momentum and position exists. That is not our current interpretation of quantum mechanics. We say that quantum mechanics tells us that the position and the momentum of the particle just does not exist before we measure them. It's not just, okay, this is the classical uncertainty relation, let's say, in a sense. So it's even existing in classical physics. But the quantum physics, quantum mechanical, the Heisenberg uncertainty relation tells us that the position just doesn't exist. The momentum doesn't exist until we measure it.
Bu hocam sadece position'da mı kalıyor yoksa yani diğer etkileşimler için de geçerli mi? Maçsal momentum. Bunları da katabilir miyiz? Dirac mesela bunu söylediğini hatırlıyorum.
Well, let's look at the energy-time uncertainty relation. Well, we know that E is equal to h nu. How do you measure the frequency of a wave? No, just consider an arbitrary wave, not necessarily a particle. Forget about quantum physics for the time being. You have a wave. How do you measure its frequency? You look at the period. How do you look at the period? Well, how do you know that there will be even more consecutive peaks? Well, you see, let's say that you have a wave that has this shape. So here you have a peak, here you have a peak, and I'm sure you will agree that this is not the period of this wave. It's not the period. Any other ideas? How do you measure the frequency? C over lambda. How do you measure lambda? Well, to start with, how can you know that a wave is harmonic?
Can we look at the waveform?
What do you mean look at?
Can we observe and plot it then?
Well, let's see. We observe it. Let's say this is what you observe. Is this a harmonic wave? No, answer my question before asking new questions. Yes. Is this an harmonic wave? Yes. Is it?
Maybe.
Why? Because I'm asking? We don't know. We cannot be sure. You see, well, in fact, you can sure. You can just see what I had plotted. It's not a harmonic wave. You see, it's no longer oscillating. And you don't know what happens afterwards. Maybe it will go like this. This is not a harmonic wave anymore. But still, you can get an idea. You see, to measure the frequency, you just count, let's say, You look at the wave. For a time, let's say delta t. You observe the wave, and you see that it is oscillating. And how do you determine the frequency? Well, the frequency is the number of peaks per unit time. So the frequency, you just count the peaks, divide by delta t. This will give you an idea of what the frequency of this, assuming it's a harmonic wave, what it will be. Well, what about delta nu? There will be an uncertainty in nu. Well, maybe you have missed one peak, or maybe you have counted one extra. Well, delta nu will be typically 1 over delta t. Well, if you have such a wave, let's say, assuming you have such a very large wave, just like in the momentum position uncertainty principle, if you have a wave that extends through a very large volume of very large length of delta x, the momentum space wave function will be very narrow. Here, if you follow it for a sufficiently long time, even if you say this wave is not a harmonic wave, but if you want to create this wave with these unharmonicities at the ends, you just need to add many waves, but still their frequencies will be in a given range, in a very narrow range. Otherwise, you cannot get these oscillations in between. And that uncertainty in the frequency will be typically 1 over delta t. But then there is an uncertainty in the energy. This is h delta nu, this is h over delta t. Or delta E delta t should be somewhere around h. If you want to be sure that it's a harmonic wave having a definite frequency, if you want to be sure that it's a harmonic wave, you have to wait infinitely long. Because if you don't wait infinitely long, maybe at some point it will be just cut off. It's no longer a harmonic wave. So delta t should basically go to infinity. And only if delta t goes to infinity, then you can be sure that delta E is 0, and hence it has a definite energy. Now, before we were also discussing that maybe energy conservation is violated. It's because of this. You see, to make sure that energy is conserved, you have to watch the value of energy at every time for infinitely long. Only in that case, delta E can be 0. Otherwise, if you look at your system for a finite amount of time, that will be delta T. But that means you don't know definitely the energy. So delta E is no longer 0.
Bu durum simetrik kırılımları açıklar mı hocam?
No. Questions?
Enerji difference'ın sonsuz olması ne anlamına geliyor? Enerji difference'ın sonsuz olması ne anlamına geliyor?
Nothing. I mean, you see, it basically means, you are essentially looking at the other limit, delta t goes to 0. You see, if you don't, delta t goes to 0, basically that means you are not measuring anything. So you don't know anything about the energy. Or if you took a very short time to create your system, then it cannot have a definite energy. Let's do some applications. Now, we had studied the particle in a box. And we said that, okay, if my box has a length L, then the possible values of the k vector was integer multiples of pi over L. So it basically means that my wave should fit in, half of my wave should fit inside, or all of the wave should fit inside, etc. Well, essentially it told us that L should be an integer multiple of lambda over 2. This was the one of the results we had. Otherwise, the particle cannot, the wave corresponding to the particle will not fit inside. And so h bar, the momentum of the particle is n h bar pi over L. So the kinetic energy of the particle, it doesn't have any potential energy inside. This was equal to p squared over 2m, or h bar pi over L squared 1 over 2m times n squared. N can take values 1, 2, 3, etc. Do you remember? Now let's look at the same problem from the perspective of the uncertainty principle. What is delta x for this particle? I know that the particle is inside my box, but I practically don't know anything about the position of the particle. So delta x is kind of L. It's somewhere inside, but I don't know where. Well, if you like, you can also take L over 2. But it doesn't really matter too much. What about the momentum of the particle? Uncertainty in the momentum of the particle. Well, this will be larger than or equal to h bar over 2 delta x, or h bar over 2L. Now, if you ask the question, what is the minimum energy of this particle? Well, it only has the kinetic energy. The minimum energy would correspond to the minimum momentum. But you see, if the momentum of the particle is 0, then it cannot have any uncertainty in its momentum, because it cannot be negative. So the momentum, the magnitude of momentum, should have at least equal to delta p, so that we can talk about some uncertainty in its momentum. So this will be equal to h bar over 2L squared times 1 over 2m, h bar squared over 4ml. That is, the uncertainty principle predicts that if you put a particle in here, its minimum kinetic energy should have that value. It should have larger than that value, let's say. It's the minimum possible kinetic energy. Well, let's compare it with the previous expression. The difference is pi squared over 2. Within a factor of 5, you can predict the minimum energy the particle can have in a box. And in fact, if you put this 1 over 2 factor, so here you will get L over 2, so there is no 2 over here. No, this is sort of 8. Now it's just 2ml squared. Now it's even a better approximation. You see, delta x is equal to, let's say, x0 plus minus delta x. So 1 over 2 would probably be a better approximation of delta x. So you just put it over L over 2 here, so you would end up having h bar squared over 2ml squared for the kinetic energy. Much better. And now it only differs by a factor of pi squared, 9. Before it was something like 18. Now it's a factor of 9. Not great, but not bad. If you cannot do anything else, This gives you an idea about the minimum energy. Let's look at the harmonic oscillator. Well, the energy of the harmonic oscillator is just p squared over 2m plus 1 over 2m omega squared x squared. And let's see, classically speaking, the particle of a given energy will just go back and forth, let's say between those two limits. Let's say that this distance is A, the amplitude of the oscillation, the classical oscillator. Then the uncertainty in x will be something like A. It's going up and down. The uncertainty in momentum will be h bar over 2a. H bar over 2. This is the minimum possible uncertainty in momentum. Well, you can say that this is the position, this is the momentum. Typical values of the position of the particle, typical value of the momentum of the particle. And then the energy of the particle will be p squared 1 over 2m times h bar squared over 2a 4a squared plus 1 over 2m omega squared. No, sorry. This is x. 2m x squared. This is the typical value of the energy of the particle in the ground state. Well, what is the minimum value? Well, you just take the derivative of the energy with respect to x, or if you like a, you will get minus h bar squared over 4mx cubed plus m omega squared x. This should be equal to 0 to get the minimum. Well, this tells us that x to the 4 should be equal to h bar squared over 4m squared omega squared, or x squared should be equal to h bar over 2m omega. Well, what is the minimum value of the energy? 1 over 8m h bar squared over x squared is h bar over 2m omega plus 1 over 2m omega squared, and x squared is h bar over 2m omega. Well, let's see, this cancels this m, this cancels one of the h bars, so you get 1 over 4 h bar omega. This m cancels this one, this cancels this one, you have plus 1 over 4 h bar omega. H bar omega over 2. Well, in fact, this is the exact value in this case.
Hocam, kutunun içindeki minimum enerji parçacığa bağlı değil diyebilir miyiz? Eğer bir kutu varsa ve belirli bir wave varsa sadece o wave'e mi bağlı oluşuyor?
Well, let's see, if you are talking about particle in a box, you estimate the kinetic energy to be inversely proportional to the mass of the object. So there is mass dependence over there.
Harmonic oscillator da aynısı olmuyor.
Well, let's see what happens in the case of the harmonic oscillator. You see, the coefficient of this one depends on m. So omega will depend on what particle you have. So this uncertainty principle, okay, on one hand it says to you that you cannot know everything because there is nothing to know actually. But on the other hand, it allows you to make some estimates about the possible minimum energies. You see, one thing to consider is if the particle has, you know that the particle has zero kinetic energy, then that would tell you that the momentum is zero. But momentum zero means that you definitely know the value of momentum. But that will tell you that you have no idea about the position of the particle. The particle can be anywhere. Read it backwards. If you know that the particle is in some volume, then delta P cannot be zero, and hence it cannot be at rest. So the kinetic energy definitely has some value. It cannot be zero. This is called the zero-point motion. Even at absolute zero, quantum mechanics tells us that the particles will be moving. They will not be at rest. So you see, quite often you will hear that the temperature is a measure of the average kinetic energy of the particles. That would say you that temperature is in the T is equal to zero limit, the average kinetic energy should be zero. But that violates the uncertainty principle. When you actually go to zero temperature, approach zero temperature, still the particles will be moving. That is absolute zero. I'm not talking about 0 degrees Celsius. Any other questions? Wait for 2 more years.
Örnek olarak momentumun sıfır olup da pozisyon değiştiren bir şey var mı çevremizde?
Well, you see, suppose you create, in our everyday life, in our everyday life, whatever we see is localized in a given finite volume. So delta X is definitely finite, so delta P is definitely finite. Well, let's put it some numbers. What is your mass?
80.
Let's say that M is 80 kilograms. Your speed? Let's say 0.1 centimeters per second. Well, he has a momentum. You see, he's moving his head, he's moving his arms. So he has a momentum. So eventually I'm trying to calculate the momentum. So, and this will be something like 10 to the power minus 4 meters per second. So his momentum is definitely non-relativistic. So his momentum will be something like, how much? 8 times 10 to the power minus 3 kilograms meters per second. That is his typical momentum. What is his uncertainty? Well, h bar is 1.054 times 10 to the power minus 34 joules second divided by 8 times 10 to the power minus 3 kilogram meters per second. So uncertainty in his position is something like 10 to the power minus 32 meters. Do you remember the typical size of the atom? 10 to the power minus 10. You see, when I look at him, I see his position. I'm definitely sure about his position, but that doesn't mean that I am actually measuring delta X to be 0. I'm just saying that my delta x is much larger than, in fact, this one. If I try to measure its position, I cannot do better than the radius of an atom. So already in your own positions, there is an uncertainty in the position.
How could we say that his momentum is the uncertainty in his momentum?
Well, his momentum can be larger than that. But how much larger? Well, that is his momentum, the magnitude of his momentum, let's say. But the uncertainty cannot be larger than that. Because you see, uncertainty is plus minus the uncertainty. Magnitude cannot be negative. Well, let's look at a typical atom, or the typical electron. So at least this argument over here should practically convince you that what we observe in everyday life doesn't contradict this uncertainty principle. Of course, you don't always look at somebody who is 80 kilograms. Maybe you will just take one raisin or one small grain. It will be, I don't know, it won't be 80 kilograms, but let's say 0.1 gram. 0.1 gram is just 8 orders of magnitude smaller than this one. You will complain that you know its momentum and position exactly, but I will say that your P or delta P, let's say, will be 5 orders of magnitude smaller than this one. Delta X should be larger than this one by 5 orders of magnitude, but still you won't reach the size of the atom. So for macroscopic objects, this uncertainty principle, although it is there, it's not really too much relevant. It's the uncertainty given by the uncertainty relation is larger than what we can measure. Let's look at an atom, electron. Well, what's the mass of an electron? Let me just look up. So it's approximately 9 times 10 to the power minus 31 kilogram. In the atom, typical speeds of the electron. Do you know the typical speeds? Not really, 0.1c. No, 1% the speed of light. So it's just 8 times 10 to the power 6 meters per second, typically. The momentum is, let's say, 10 to the power minus 25, 10 to the power minus 23 kilogram meters per second, typically. And the uncertainty in its momentum would be typically at most this much. It cannot be much larger than that. Well, what about the uncertainty in its position? H bar over 2 delta P, 1.054 times 10 to the power minus 31 joules second divided by 10 to the power minus 23 kilogram meters per second. So delta X is typically of the order of 10 to the power minus 10 meters. Or if you like, 11. Now that is the size of the atom. So for an electron, in an atom, the uncertainty principle will be important. For us, for macroscopic objects, irrelevant maybe, but for an electron in an atom, it will have a very large influence on its properties.
Bu değer elektronun neden çekirdeğe düşmediğini açıklar mı?
It will eventually.
Çünkü konumundaki belirsizlik sıfıra iner eğer çekirdeğin içinde olursa.
Well, it is saying that the electron is inside the nucleus would increase the uncertainty in its position by a couple of orders of magnitude. So its momentum should increase by a couple of orders of magnitude.
Another uncertainty relation which we will face with.
Many, but not now, not this year. Now, you will be generalizing this uncertainty relation to what we call the incompatible observables. For example, position and momentum are incompatible observables in the sense that you cannot observe both of them at the same time.
For macroscopic.
For any object, in fact. But the uncertainty for macroscopic objects will be beyond the limits of measurement. For microscopic objects, we will be seeing, its properties will be determined by these uncertainties. There will be an uncertainty relation between the direction of an object and angular momentum, for example. And well, there was a question about having a particle whose momentum, zero uncertainty, and having a momentum or something like that. Anyway, just keep in mind, when we are talking about the uncertainties, let's see. It is possible that you create a wave packet that looks like this. Then with time, it will move forward so it's just the particle, you can say that the average position is moving forward. But you see, to create such a narrow packet, we said that you should add many waves with different momenta. Well, some of those waves can have a momentum in the opposite direction, can have a negative momentum. So even if by measuring the position of an object, you know that on the average it is moving in one direction, if you measure the momentum of it, it might be pointing in the opposite direction. Well, the measurement is itself a problem because you see, Newton says that you can study the motion independent of the observer. Measuring the position will not change it. But what quantum mechanics tells us is that if you measure the position, it will change the system. Now, why this is important, I don't know if we had discussed it, but for example, what is force? We say that, for example, the electromagnetic force is created by exchanges of photons. So if I'm a negative charge over here, you are a positive charge over here, I constantly emit photons. You constantly absorb, I also constantly emit and absorb photons. You constantly emit and absorb photons. If we are nearby, you will be absorbing some of the photons that I emitted, and I will be absorbing some of the photons that you emitted. But photons have momentum. So basically, by this emission and absorption of photons, we are transferring momentum to each other. So our momentum will be changing. Well, momentum change is what we call the force. So that is how the electromagnetic force comes into the game. If we are both negative charges, then we will repel each other. That's kind of intuitively easy to understand because the photons, if they are to reach you, they should go in that direction. They have a positive momentum. So your momentum will change in that direction. But what if you are a positive charge and I am a negative charge? the photons should go there in that direction, but your momentum should change in this direction. So the photons moving in that direction should have a momentum in the opposite direction. Then you are saying, how come? Well, there are basically two different interpretations of this phenomenon. Either you say that, okay, the photon has a momentum. So where is this photon? Everywhere. That photon is covering space. So it's moving in that direction. It might be moving in that direction from behind him. So they will transfer a momentum to this in this direction. So we will be attracted to each other. Then you say, okay, that doesn't make sense. The photon should appear where I am. I'm emitting the photon. Then you are saying that I know the position of the momentum, or position of the photon. Initially at least, it's over here. And eventually it will be over there. So I know the position. What about its momentum? I don't know anything about its momentum. It can be positive, it can be negative. So even if we are in this distance, let's say, I can transfer a momentum to you in this direction. Why shouldn't it be?
Çünkü sadece sizden geliyor. Tamam, benden geliyor ama uzak. Çünkü
Yes. No, I mean, I am losing that momentum, you are gaining that momentum. So that's a transfer. That's why it's conserved. Anyway, so next week we will start the atom. How can we understand the atom itself? And we will come to your question about the stability of the atoms.